Good evening all of you, and here is a crazy technique to reduce your time and calculation and make your life easier, safer and faster. And this is generalization and this is general integration by parts, and here we go with the basic idea. As we know, if we need to integrate two functions u and b as a function of x, so from integration by parts we have u integral of b dx minus integral of course minus integration of differentiation of first block into whatever is there, that will copy paste. Is we can use generalized integration by parts, and it goes like this: you leave one, integrate the other function, minus differentiate the first, integration of other, plus differentiate again the function which we got previously, integrate the second one again, minus differentiate u thrice, integrate b 4 times, plus and so on and so forth. In a cool way I can write leave u, integrate b, let's call with this symbol b minus 1. B minus 1 is integration of b 1 times, minus u1 b minus 2 plus u2 b minus 3 minus 3 b minus 4 and plus minus. क्योंकि इसमें I can clearly see if I select the function u in such a fashion so that its derivative is eventually killed. तो अगर मैं कोई भी एक ऐसा फंक्शन u लूँ जिसका बार बार डिफरेंशिएशन, लेट्स से nth derivative becomes 0 at that point, so the process of generalized integration by parts will end. तो यहाँ पे x square will be such selection, तो I'll select x square as first function, integration of second e का power x minus, अब इसको डिफ्रेंशिएट करो फर्स्ट वाले को और दूसरे को इंटीग्रेट करो, सो एक्स स्क्वायर का 2x, इंटीग्रेशन ऑफ ई का पावर एक्स जी का पावर एक्स, प्लस अगेन इसको डिफ्रेंशिएट करो और ई का पावर एक्स को इंटीग्रेट करो, माइनस 2 को डिफ्रेंशिएट करो 0. So the final answer to this problem is x square minus 2x plus 2 e to the power x. Now you can do this method really fast. Suppose if I have e ka power x into x ka power 4 dx. So I can tell e to the power x, because integration of e ka power x is going to be e ka power x, x4 minus its derivative 4x cube plus 12x square minus 24x and plus 24. And that's the answer for this problem. You might not be happy, so let's try the second question. Suppose we have to integrate x cube plus 2x minus 1 into cos 4x. So if I've got this, again I'll use the same funda. So this time again I'll select this function as my function whose derivative I'll be taking. So x cube plus 2x minus 1, integration of cos 4x sin 4x over 4, माइनस इसको डिफ्रेंशिएट करो, सो 3x स्क्वायर प्लस 2 into integration of sin 4x by 4, so that will become minus cos 4x by 4, and 4 was already there, so 16. Next term will be again plus differentiate 3x square plus 2 6x, इसको इंटीग्रेट करो, so minus sin 4x by 4 cube will come, again minus 6 will differentiate 6, again integrate that part, so sin x ka minus cos, so that will become cos 4x by 4 to the power 4. Now if we'll collect the term, so finally what we are getting is 1 by 4x cube plus 13x by 32 x minus 1 by 4 into sin 4x plus 3 by 16x square plus 13 over 128 to cos 4x plus constant. So you see how we have killed this monstrous problem just in single line. The beauty of this method is not only limited to the case when p of x is a polynomial, because of course if I select polynomial to be a function whose derivative will eventually die after nth derivative, even we can apply this idea for a non-polynomial function. For example, let's say we have e to the power 2x and sine 3x dx. by 2, so by 4, and now plus, it's going to be 3 into 3 minus sine 3x, and this integration is going e to the power 2x by 8, and so on and so forth. Now we can clearly see this integration at this step. What we can do is at this step what we can do is this integration, because now this method will continue forever. So if I want to stop at the third method, I have to take integration of this, right? So this integration is nothing but minus 9 by 8 e to the power 2x sine 3x dx integral, and this is back to I. So if I suppose this is I, this is back to I. So hence we got 13 by 4I is half e to the power 2x sine 3x of this integral. Again, in one line, how we can do it? So I can leave x square minus x cube, integrate cos wala part, so that's going to give me sine 4 pi x over 4 pi minus 2x minus 3x square into integration of this, which is going to be minus cos 4 pi x by 4 pi whole square. Then we have plus 2 minus 6x, integration of this part together with minus sine 4 pi x by 4 pi whole cube, and now we have again minus of minus 6, integration of this guy going to be cos 4 pi x by 4 pi to the power 4. So you can clearly see what we are getting is, if we'll combine all the terms, so it's going to be minus 1 by 16 pi square after finally evaluating from 0 to 1. And if we'll put the value, it's very easy because sine of n pi is 0, and plus 6 times of 1 minus 1 by 4 to the power 4 pi to the power 4. So this term goes, and the final answer is minus 1 by 16 pi square. So I hope you must have enjoyed the method, because for otherwise, if you have to do integration by parts on a repeated loop. But this is not the end of the story, and there is one more cool questions behind this application. And here is a different kind of tricky application. Let's say if we have to integrate x tan inverse x dx. So clearly the usual way of integrating will be, we'll leave tan inverse x, we'll integrate x, which is x square by 2 minus differentiate tan inverse x plus x square into that integration x square by 2 dx. Right. And now it takes a little bit of time. You can add and subtract 1 to evaluate this. But here is a cool way. And the cool way is, since I am free to select any constant whenever I am integrating constant, I'll select so that my purpose will be served. So next term will be half times integration of x square, which is coming because of this term, and we have 1 plus x square dx. Here, instead of selecting integration of x dx as x square by 2 plus 0 and putting limit of constant in the integration of constant in last, here instead of selecting x dx integral as x square by 2 in the beginning, what I'll do smartly is I'll select x square plus 1. And using this selection, the motivation is coming from denominator. It simply goes, and the answer is tan inverse x into x square plus 1 by 2 minus half x plus constant. And now this constant will take care of all our rituals, because in this step, integration of x dx, someone could have made x square by 2 plus lambda, and again, so overall effective lambda will come at the end. Okay, so we can always select the limit of integration, the integral constant, in such a fashion so that the second integration becomes easier. One more cool examples of this will be probably if we think of, let's say, integral of ln x plus 2 dx. So again, usually we'll leave ln x plus 2, we'll integrate 1 dx. Now again, instead of integration of 1 dx as x, I'll try to select x plus something such that a differentiation of this becomes x plus 2. Now if I'll put x, again I need one more calculation. So this time, instead of integral of 1 as x, I'll select x plus 2 everywhere. And that makes our life so simple. So it's x plus 2 minus x plus constant is x. To get the full glory of this question, let's take one more. And that's interesting. Let's say tan inverse root over 1 plus x dx. Again, as usual, I'll start with 1. So we'll write tan inverse root 1 plus x into integration of 1 dx. I'm writing x plus something that will be demanded from the next expression. Tan inverse differentiation is going to be 1 by 1 plus root 1 plus x whole square into 1 by 2 root 1 plus x dx. Now, and we have to write x plus something. Now here, what should I write? Clearly you see in the denominator we have x plus 2 will be coming. So I'll select x plus 2 into picture. And that is really crazy because this simply gets kicked off and the final answer is x plus 2 tan inverse root 1 plus x minus dx by 2 root 1 plus x becomes this plus constant as the answer. I hope you have got the essence of the question. The essence was, whenever we have 1 dx, I am free to write x plus some lambda. And the selection of lambda will be dictated by the second term so that the integration gets cancelled and my integration by parts becomes very tricky and healthy to operate. Thank you. Please do like and subscribe.